So the work we provide here is formalising some cryptography. In particular, we're interested overall in multiparty computation, MPC, but here we focus on the Oblivious transfer protocol, which is sort of a very low-level primitive that's used a lot inside MPC. So first, we'll just outline what MPC is and this sort of Oblivious transfer, and then provide a little bit of motivation as to why formal methods are needed in this area. Then outline what we do in this work, and then detail parts of it. So we'll look at an OT protocol, and hopefully we'll see how this works and how we can improve security with respect to it. So what is multi-party computation? So it was introduced in the 1980s by Yao, where he sort of considered the problem of lots of millionaires sitting around at lunch, and they want to decide who's going to pay for dinner, pay for lunch. And they decide that the most wealthy of them will pay, but they don't want to just tell each other their wealth. They want to compute this function jointly, but securely. So they want to see who's the most wealthy, but they don't want to disclose their inputs to each other. So initially, I think this was a sort of a bit of an intellectual curiosity, but now we're seeing in the crypto world that it's becoming a real-life problem that's happening. So everyone cites the famous sugar beet auction in Denmark. This was one of the first applications of MPC, but we're seeing more and more that it's become used in the real world. So I think it's important that we consider this formally. Now, the protocol, the sort of primitive that we're looking at here is Oblivious transfer. It's really at the heart of MPC, and we can see this function here describes it formally. But what we're looking at is a two-party protocol between a sender and a receiver. So this sender holds two messages, M0 and M1, and this receiver a choice bit, sigma. And the output of the protocol is that the sender learns nothing, but the receiver receives the bit it chose. So here, M sigma's transferred across. And we'll see, hopefully, in the protocol later how this happens, the sort of tricks that we can use to do this. There's other flavors of Oblivious transfer, sort of the most general being K out of N, so we transfer K out of N messages. Or 1 out of 4 is also quite commonly used. So as a result of this Oblivious transfer stuff that we want to consider, here we work in the two-party setting. So although we're working in multi-party computation, here we really focus on the two-party setting. So a little motivation. So in 2004, Butler and Roggeway wrote this. They said that in their opinion, lots of cryptographic proofs have become unverifiable. And that the field may be approaching a crisis of rigor. Now, there's a number of different quotes that sort of run along the same lines. But why might the proofs in cryptography be difficult? Well, there's lots of edge cases. Often the proofs are getting quite complex, quite long. So in general, they were finding that they're becoming quite hard to verify. And a bit more sort of recent motivation, Jonathan Katz in his talk at Crypto last year, his invited talk, focused on MPC. And I sort of try to paraphrase his slides very quickly here, but he basically said that MPC is moving from theory into practice. So it was this intellectual curiosity, and now it's really becoming sort of seen in the real world. And in the proofs, in the theoretical proofs, often low-level details are omitted, so we have these folklore or obvious results that aren't really considered. Another thing he highlighted was that performance optimizations that are applied during the implementation are not actually considered in the theory. So again, this is kind of this difference between theory and practice. And that this end-to-end security that everyone always likes is kind of missing. So back to this talk, perhaps formal methods can alleviate some of these problems. Clearly, all proofs have to be sort of complete. There can be no missing or obvious things left out. And perhaps code generation, which sort of formal methods often alludes to, can help with this goal of end-to-end encryption. Yes. So in this work, we use Isabelle Hol, the theorem prover, and in particular, we use CryptHOL, which is embedded inside Isabelle to do our proofs. So a quick overview on what CryptHOL is. So it's embedded in Isabelle, and essentially it provides a probabilistic programming framework. If you think about it, cryptographic protocols really do some sampling, some assignment, so they can kind of be modeled, and we'll see in a minute how they can be modeled as probabilistic programs. And CryptHOL is based on this data type, the SVMS data type. So this stands for the sub-probability mass functions. But here we can really think of these as just probability mass functions, but they don't have to sum to 1. In cryptography, this can be used because maybe an adversary refuses to output something. So sometimes we have to lose probability. So that's all we're talking about here, but really just think of these as probability mass functions. So what do we actually do in this work? So we consider two different adversary models. So we've got the semi-honest adversary model on the left and the malicious model on the right. And in this talk, we'll just look at the semi-honest model. And as you can see, we've done a lot more work in the semi-honest model because we found things get complicated very quickly in the malicious model. And in this talk, we'll focus on this kind of left-hand column. So first, I'll show how we can define two-party computation in the security definitions we want. And then we'll look at this Oblivious transfer protocol that uses extended trapdoor permutations. This is a sort of general construction. An extended trapdoor permutation is this general mathematical sort of object permutation. And we were able to prove a general proof about this and then instantiate it for the RSA instantiation, which is this. So semi-honest security, this is the model. So we're looking at this top left box here. So the semi-honest model assumes that the corrupted party, so in a two-party setting, we sort of assume one party is corrupt because we don't have any guarantees if both are corrupt, really. So the party that's corrupt, it assumes that it still follows the protocol transcript. It assumes that it doesn't deviate, it doesn't act maliciously. Now, this might seem like quite a weak notion of security, but it gives us this baseline. Many protocols that are secure in the semi-honest model can be transferred to the malicious model and be proved secure there with sort of different techniques to sort of improve their security. And what it does ensure, there's no data leakage. So a party that's sort of corrupt that might be really analyzing all the messages that are sent to it, this model guarantees that it can't learn anything from these messages about the private input of the other party. So how do we do this? Well, we do this exactly the way I just said. So we consider this real view of the party. It's the transcript that the party sees in the execution of the protocol. And this is what the corrupt party is analyzing if it wants to learn something. And what's the idea of security here? Well, we want to show that the real view of the party can be simulated. It can be simulated without using the other party's input. So we've got this secret input. If we can show that this real world is somehow indistinguishable to this ideal world where we don't use the secret input, then we have this notion of security. So it's a bit like what we saw in the talk earlier, in the invited talk, this ideal and this real world. So these are what the paper definitions look like. And I don't want to spend too much time looking at the details of these, but this is what you'll see on paper. That pi, which is a protocol, securely imputes f, this functionality, this sort of what we want to compute, in the presence of semi-honest adversaries, if these simulators exist. Now, they're meant to be polynomial time algorithms, but at the moment, CryptHOL doesn't reason about polynomial time, so they're looking to build this in, and once it is, I think we'll be able to adapt this very easily. So at the moment, we just manually verify that our simulators are polynomial time. They're all relatively simple, so sort of just checking them is okay for now, but it's not ideal. And then what are these statements saying, these security statements? So we consider each party in turn. Firstly, we say that for party one, we have this simulator which takes the input of this party, which would be x, and it's allowed the output of the party also. It's sort of a technical detail. And this sort of distribution on the transcript in this ideal world is equivalent to the real world. So here we've got this idea that both these ideal and real worlds are the same. And we have exactly the same definition for party two. So how do we actually sort of formalize this in Isabelle? Well, we're able to use this locale system to make abstract definitions. We just form a locale like this. So a locale, we can just think of modules. So what do we fix? We fix things like the functionality, the protocol, and then these real and simulated views that later we'll instantiate. And this is sort of actually how we do it. So I mentioned earlier that we can't reason about polynomial time yet, but hopefully when it's built in, we will be able to. And we reason with advantages. So the advantage that a distinguisher has of telling this sort of real world and this ideal world apart. So this real world we've already defined, we've already fixed what this is. This ideal world, if you remember I said about this other input the simulator is allowed to take. So we define this on this first line here. And the simulator, if we read from sort of right to left and work our way backwards, we have the simulator that takes in this first message, the message of the party it's allowed to see, and the output of that party. But we need to sample that output from the functionality. So we use this binding operator, so we sample from the functionality and give it to the simulator. So this is how we define the ideal world. The key being that the sort of secret input isn't ever seen in this case. And then this advantage is just defined as sort of the difference in the probabilities. So we have the probability when the real world is given to a distinguisher, the sort of transcript of the real world is given to a distinguisher, minus the probability of when the ideal world is given to the distinguisher.
Okay, so now we'll move on to actually try and see a protocol that observes this Oblivious transfer protocol. Did we skip one? Okay, so we just first need to sort of see what an extended trapdoor permutation is. And we can think of these essentially as a set of permutations. The protocol that we look at is, in this example is quite a well-known protocol by Goldreich in the mid-80s. So we first formalize these ETPs, these extended trapdoor permutations, in a general way, and then we're able to instantiate the proof, use Isabelle, use the module structure to do this. Okay, so what is an extended trapdoor permutation? So it's a collection of permutations, these sort of F alphas, along with these four algorithms, I, S, F, and F inverse. Now, F and F inverse are sort of just the canonical projections of little f. And they can be seen as a sort of collection of one-way permutations. So we need to have this idea of a trapdoor in there. So what does I do? Well, this algorithm I samples an index of the permutation alpha, and then the corresponding trapdoor. So this sort of shows which function we're actually using. And then S of alpha samples a uniform element in the domain of this permutation. And then F and F inverse perform these mappings here. So to reason about these extended trapdoor permutations in general, we make these 5 assumptions. There's a couple more technical assumptions that I don't want to go into about this sort of sub-probability mass stuff. We have to make sure that some things sum to 1, some of the probabilities sum to 1. But we've got sort of 3 fairly mundane ones, that the domain is equal to the range, and that we have a finite range, and that the range is non-empty. And then sort of, I guess, the slightly more interesting ones where we have a bijection, and then that the inverse of the function applied to the function gives us what we want. This is kind of, with the trapdoor, this is what we want here. And the key sort of security aspect to an extended trapdoor permutation is this hardcore predicate B. This is the bit of the inverse that we know cannot be guessed. And for RSA, for example, this is the least significant bit. But this is the sort of security property that we need on these extended trapdoor permutations. And we'll see it in the protocol in a second. So what's actually happening in this protocol? So it's a relatively short protocol, so it's quite succinct, which is nice. And it sort of follows the general theme of how Oblivious transfer, how this kind of magic idea happens. So first, we see that the sender on the left-hand side holds 2 messages, M0 and M1, and then samples alpha and tau. So this is sort of, I guess, in some way creating some keys. It sends alpha across to the receiver. The receiver now knows which function it's working with. The receiver then samples 2 things from S, so using the same algorithm S, but importantly, only sort of uses the function, only applies the function to 1. So this is sort of the key to this side of the protocol, because the receiver now knows the inverse of this F, which in theory is hard, but it doesn't know anything about the other one. So it sends these across, these Y0 and Y1 across, where P1, the sender, then inverts both. But we can see here that one of these is kind of meaningless, because only one of them was acted upon by F on the right-hand side. And then the sender sort of encrypts both messages. So it encrypts them in the same way by using this hardcore predicate B. So it sort of XORs this with the 2 messages, and then sends them back across. And if you stare sort of hard enough, you'll see that this decryption on the bottom of the right-hand side gives you the desired output there. What happens with security here? Well, let's assume that party 1 is corrupt, and it's trying to look at all the messages it receives to learn something about the input of party 2. Well, all it sees is Y0 and Y1, and we can see that they come from an identical distribution. And because F is a bijection, we can use a sort of one-time pad property there. So that's relatively simple. And we know that party 2 learns nothing of the other message that it's not allowed to receive, because it can't guess this hardcore predicate B. Like this was the idea behind what B is, the security property of B. You can't guess it. So it can't ever guess the second message. So I don't want to go into details about the security proofs really, but just give you a flavour of what we're dealing with here. So this is for party 2. We define the real view and then the simulated view. And these are the sort of probabilistic programs that we're dealing with. So they don't look that long. However, the proofs become semi-long.
So the actual constructions we're using are not that complex, but also hopefully you can see that this simulator is fairly obviously in polynomial time, although we don't actually verify that because we can't yet. And how do we actually show security? Well, we show for party 2, we have this reduction. So we show this, that the advantage of party 2 is less than 2 times the advantage of this hardcore predicate sort of security property, which we've also had to define. So if we've just shown this reduction to a hard problem. And for party 1, we show perfect security. This just means that the real view and the ideal view are the same, and they're equal. So let's have a think about the RSA instantiation now. So the previous proof was just for this general extended trapdoor permutation. It was fairly simple. We just fixed some assumptions in a module, in a locale, and this proof went through. But now we want to instantiate it for the RSA function. So the RSA function's written there. And here we can sort of use Isabel's module system to get this security proof for free. And all we have to do is prove that the RSA function is actually an ETP in this respect, with respect to these initial assumptions. And these security results read exactly the same, except we now have this done. Sort of an interesting note, we also did the RSA proof from scratch beforehand, because I was being naive. And then, but using the general proof, we were able to delete about half the proof, which was nice. I guess that's a sort of small win for formal methods. It was interesting. The most difficult part of the sort of instantiated proof was finding a detailed enough paper proof that the RSA function was in fact a bijection. It's always sort of cited as a very trivial thing, but actually finding detailed proofs of these that's enough to formalize was relatively difficult. We had to sort of go searching for that quite a bit. So what have we learned from this work? So we haven't touched on the malicious model here, and the semi-honest model was okay to do, but we found once we got to the malicious model, things really got complicated more quickly. The reasons for this, probably because the protocols get more complicated. The protocols just get longer because you have to do more things. You have to ensure that adversaries that are doing arbitrary things can't damage, can't learn any information. So things get complicated quite quickly. And here we found that even detailed paper proofs are only just enough. We had to sit down with cryptographers to try and work out what's going on here. So I've been reading these security proofs for maybe sort of 3 years throughout my PhD, and I'm getting to a stage where I can just about read these now. So properly, but often sitting down with a cryptographer, you have to sort of decode what they've written. But this was rewarding. We found out that this worked. So perhaps one takeaway from this is that we need to come up with some sort of common language maybe that crypto people can help to write their proofs in, or at least a more standardized paper proof language for cryptographers may help. And I think that's all I have to say. If this wants to work, it should say thank you.
Questions?
So in our formalization of MPC in EasyCrypt, we found that non-interference was a very useful property. Have you used similar insights?
No, we didn't. So your work here used EasyCrypt to do this. We found for the malicious setting, and perhaps we can discuss later, that we were able to follow the paper definitions of Lindell and Goldreich relatively closely. So we didn't necessarily need to use this. It'd be very interesting to discuss why this was the case in EasyCrypt compared to Isabel. So yeah, I don't have a better answer from that at the moment.
Thank you. Follow-up question, if I may. So do you have in mind what kind of language we should use to communicate with cryptographers? Your last bullet point.
Yes. So I guess it's this notion of probabilistic programs. So when cryptographers define their security definitions, they don't really ever talk about probabilistic programs, but that's really what they are kind of talking about. So maybe even just as simple as using some of this sort of do notation, where at least it's really obvious what's happening. Okay, they can use arguments in the proof that are nice, but maybe just something that states out what the simulator is and what this other thing is. Because often you have simulators that are described not in algorithmic form, but are just described in text. And this is often very hard to pick out exactly what's happening here. So possibly that.
So maybe a bit related to your question, it seems like from how you're describing it is that this is essentially like an Isabel translation of the proof from the paper almost.
Yes.
Do you think there is room there for automation? And if that's the case, do you think that that's why things like, you know, fancy program logics like sort of EasyCrypt are what needed for something like that?
So, in terms of automation of the whole proof, I think you'd struggle to. You have to really point Isabelle. Obviously, we used automation when we were using Isabelle. You know, you use Sledgehammer in your everyday work. But I think actually getting automated proofs for the whole way down, the arguments are not that they're not that easy to follow. For a human, they're quite easy to follow, but I can't see how a computer at the moment, unless anyone has any bright ideas about how to do that, how they can reason about these, because the simulators are not that trivial. They're not that obvious.
Just a tiny other question. So this is just one particular OT protocol. You think any of this could be used for like other OT, like simple OT, say, or something newer than this?
Yeah, so I think we picked this. So you have to think about when we're picking these sort of case studies to formalize, really, you're looking at stuff that's sort of simple enough to be able to formalize. You can't necessarily tackle state of the art, but you're also looking at stuff that has proofs that are detailed enough. Because otherwise, you know, you have to go and sit with cryptographers for hours to try and work out detailed proofs. So you have to sort of handpick your protocol slightly. So I just fear that for more modern stuff, maybe these proofs don't exist yet that are detailed enough for us to work with.
I think we can fit in one more short question while maybe the next speaker plugs in.
So I have one question regarding the problem that you mentioned about the complexity of proofs.
Yes.
So there's one technique, this game playing techniques, which basically tries to tame the complexity. I mean, how does your proof proceed? Does it proceed like a sequence of like changes, or it's just like a big monolithic thing with?
So you have these two sort of paradigms. You have the game playing technique and then the simulation-based thing. And cryptographers often see these in very different worlds, but actually they're quite similar. They basically involve manipulating probabilistic programs to show that they sort of eventually are equal or equal to something that you want. So yeah, I think that's it. So it's very closely related.
Okay, let's thank the speaker again.